In this lecture, we are going to answer the question, what is machine learning? I always like to discuss this first because I take a very different approach compared to most other resources you'll find. In general, I think the approach most other resources take is that they like to frame machine learning as something complex and something fancy and something futuristic and exciting. My approach, instead, is rather kind of depressing. How I want you to think of machine learning is that it's something not fancy at all, and something that only requires spatial reasoning. My goal is to make machine learning sound as dumb as possible. Here are some anonymous definitions of machine learning that I found on the internet. Let me read this one out to you. Machine learning is an application of artificial intelligence that provides systems the ability to automatically learn and improve from experience without being explicitly programmed. Machine learning focuses on the development of computer programs that can access data and use it to learn for themselves. The process of learning begins with observations or data, such as examples, direct experience, or instruction, in order to look for patterns in data and make better decisions in the future based on the examples that we provide. The primary aim is to allow the computers to learn automatically without human intervention or assistance and adjust actions accordingly. Wow, that seems pretty magical. Here's another one. Machine learning can be explained as automating and improving the learning process of computers based on their experiences without actually being programmed, i.e., without any human assistance. The process starts with feeding good quality data and then training our machines, computers, by building machine learning models using the data and different algorithms. Again, very generic, but no substance. In fact, these two definitions were so poorly written, I had to fix them up a little bit due to some obvious grammatical errors. I didn't edit them too heavily since I didn't want to lose the gist of what they were saying, but you can tell that these were not written by people who actually know about machine learning. None of this tells me how machine learning actually works. This is what I would expect if I were not a student of machine learning, in other words, just a layman, and I wanted to know about how someone completely ignorant of machine learning would view it at a high level. In other words, as students of machine learning, this is not really how you want to think of what we are doing. So starting now, you are no longer just a layman, you are a machine learning student. So instead, I'm going to teach you my dumb as possible approach, which is encapsulated by the motto, machine learning is nothing but a geometry problem. Let's repeat that. Machine learning is nothing but a geometry problem. The best way to illustrate this is by example. Let's start with an example of regression. Regression basically means you're trying to fit a line or a curve. So right away you understand that this is geometry. Geometry is just lines, planes, curves, circles, and so forth. That's why you'll sometimes hear grumpy old statisticians say things like, machine learning is nothing but glorified curve fitting. By the way, if you are a grumpy old statistician, then you're probably going to be offended by everything we do. You can take this up with Jeffrey Hinton. So let's say you're a data analyst and you want to know, how is salary related to years of experience? You might model this as a straight line, where the input x is years of experience and the output y hat is the predicted salary. As you may recall from your high school math studies, the equation of the line is y hat equals mx plus b. Here m is the slope and b is called the y-intercept. Your job, of course, is to find these values of m and b. To expand on this a little bit, here's how you would do this in the quote-unquote real world. Let's say, for example, you were a data scientist at LinkedIn or Glassdoor. So you have access to their database, and you can see, for each user, how many years of experience they have and what their current salary is. Let's call these data points x1 up to xn and y1 up to yn. As mentioned previously, x is the years of experience and y represents the salary. We'll use y to represent the true salary, whereas y hat represents the predicted salary. Both x and y are indexed by the numbers 1 to n, so there are n people in our database. Then what you're going to do is you're going to take a big piece of graph paper and plot each of these xy data points. You're physically going to draw a dot for each data point. Then, once you're finished drawing all your dots, you're going to take a line that goes through all these data points. Pretty simple, I think. And believe it or not, this is exactly what machine learning is. So as mentioned, the example we just discussed is called regression. This is where you're trying to fit a line or a curve to some data points. Now, there are two ways we can make this more complicated, and more like the datasets we might encounter in the real world. First, we might have more than one input feature. In the previous example, the number of years of experience was the only input feature. But realistically, you might measure more things. For example, you might record things like what kind of degree the person has, like a bachelor's, master's, or PhD. You might record what school they went to, what country they are from, what their age is, and their gender. All of these factors or features might affect the salary. When you do this, the object you're trying to fit is no longer a line. If you have 2 input features, then you have 3 dimensions in total, so you get a plane. If you have more than 2 input features, then you get a hyperplane. By the way, in case it's not obvious, you can't visualize anything beyond 3 dimensions, because the physical world itself is 3 dimensions. The second way we can make the regression problem more complicated is that instead of trying to fit a straight or non-curved object like a line or a plane, we can fit a curve. Many real-world datasets are nonlinear. Think of something simple like exercise. If I do 20 push-ups, will I gain twice as much muscle as I would have if I did 10 push-ups? If I do 30 push-ups, will I gain 3 times as much muscle? Of course, the answer is no. Otherwise, we'd have people doing push-ups all the time and becoming very large people. At some point, the benefit of doing push-ups is going to taper off. Now, let's turn our attention to another kind of machine learning problem known as classification. Both classification and regression are examples of supervised learning, which is going to be the main focus of this course. We will sometimes discuss unsupervised learning as well, but the main focus will be supervised learning. So, whereas regression is concerned with predicting a real valued number, classification is concerned with predicting a category. One popular example is image classification, where your model accepts as input an image of a dog or a cat and tries to predict whether the label should be dog or cat. However, in this lecture, we're going to look at an example that helps us build this geometrical intuition we've been talking about. So let's say I want to predict the risk of cardiovascular disease, given a patient's height and weight. This is a categorical problem because my prediction is either going to be at risk or not at risk. Again, this comes down to a data collection experiment. I'm going to look at all my hospital records and I'm going to write down all of this information in an Excel spreadsheet. I'll have 2 columns to represent my X and 1 column to represent my target, Y. By the way, note that it's customary to represent binary targets as the integers 0 and 1. So we would say not at risk is 0 and at risk is 1. Note that there's no reason that at risk should be 1. Just like the dogs and cats example, it doesn't matter if dogs are 1 and cats are 0, or dogs are 0 and cats are 1. This assignment is just arbitrary. Okay, so now that I've collected all my data, what am I going to do? Well, again, I'm going to plot these on a grid. On the horizontal axis, I'm going to have my first feature, the patient's height. On the vertical axis, I'm going to have my second feature, the patient's weight. Now, importantly, unlike regression, the target does not get its own axis. Instead, because it's categorical, we would represent it with color. So I might color the at-risk patients as blue and the not at-risk patients as green. Okay, so what is my model going to be for classification? Well, the simplest model again is a line. However, this line is a little bit different from our regression line from earlier. The regression line, if you recall, was the line of best fit. We are trying to get the line to be close to all the data points. Now, we are no longer trying to do that. Instead, we are trying to get the line to separate the two groups of data points, or in other words, separate the different colors. As you can see, this again boils down to a geometry problem. How do we find this line that can indeed separate these categories? One lesson that goes hand in hand with the geometrical perspective is another motto of mine: all data is the same. Let's use another example to illustrate the point. Suppose instead of working at a hospital, you now work at an insurance company. Your job is to do fraud detection, or in other words, classify instances of fraud. So again, you have two categories, fraud or not fraud. You're trying to predict whether or not a given claim is fraud. Let's say again you've collected some data points, again with two input features. Suppose these are, number 1, the amount of debt the claimant has, and number 2, the total amount of past insurance claims. And again, it's the same story. Once you've collected all your data points, you're going to plot them and color them on a grid. Your job again is to separate these data points with a line or a curve. So you see that just because we changed the meaning of the problem, we haven't changed what our actual task is. It's still to plot these points and separate them with some kind of decision boundary. A line is the simplest, but just like with regression, there are two ways we can make this more complicated. The first way is that we can have more input features, so that it's not possible to plot them on a grid that we can visualize. The second way is that the decision boundary may not be linear, in which case the model will be an equation that's more complicated than a line or a hyperplane. Importantly, however, the moral of the story remains the same. This is still a geometry problem. And in fact, for our two classification examples, the geometry problem was the same. The only thing that changed was the meaning of the numbers. Of course, machine learning algorithms don't care about these meanings, and so they are essentially irrelevant in the eyes of the machine learning model. That's why we say all data is the same. This becomes a very powerful concept in the future. For example, the same kind of model used for neural machine translation can also be used for a chatbot. The same kind of model used for sentiment analysis can also be used for spam detection. Thinking in this way essentially gives you machine learning superpowers. To summarize this lecture, the goal was to take the magic away from machine learning. You learned a very important lesson, which is that machine learning isn't magic. In fact, it's just geometry. We learned about the two different kinds of geometry problems that supervised learning can solve. The first kind is regression, where we try to get a line, plane, hyperplane, or curve to be as close as possible to the data points from a given dataset. The second kind is classification, where instead of trying to get the curve as close as possible to the data points, we try to separate data points belonging to different categories. One important lesson that goes along with this is that all data is the same. It doesn't matter if we're trying to classify risk of cardiovascular disease or if we're trying to classify fraud in an insurance company. The general problem remains the same, and it is a problem of geometry. In this lecture, we are going to answer one of the most common questions I get. That is, once we've trained the model, how do we save it for later use? For example, after training a model in Google Colab, I might want to copy that model into my production server so that other services in my company can make use of that model that I just trained. This lecture will show you how to save a model to a file and then load it back at a later time. In addition, we'll see how to download the saved model from Google Colab. First, note that this is a continuation of a notebook we were previously looking at. As usual, you can determine what notebook we are currently looking at using the title of the notebook. So if you left this notebook previously, you may want to reopen it at this point so you can follow along. Let's start with the central object that we need for this process, the state_dict. As you can tell by its name, it's a dictionary. If you look at what we get when we call model.state_dict, we can see that it's not just any dictionary, but rather an ordered dictionary. That kind of makes sense, since if you're iterating through the dictionary to populate the weights of a neural network, you would want to do that in the order that your model expects. As you can see, it's nothing but the parameters of the model. Since we just have one layer in our model, the first element is the weight matrix, and the second element is the bias vector. The next step is to save the model. We can accomplish that in just one line of code, torch.save. For the first argument, we pass in the model's state_dict, and for the second argument, we pass in a file path. I've just passed in mymodel.pt, so the file mymodel.pt will be saved to the current directory. You can see that after saving the model, when I do an ls, the file I just saved appears as expected. The next step is to load and evaluate the model to ensure that we saved it correctly. In order to do this, we first have to recreate the model the same way it was created originally. That might seem strange, since we still have to replicate the code we had earlier. This will probably make more sense to you once you've seen more complex models, which will involve defining our own classes. In those cases, you would just instantiate an object of that class, which is one line of code, which would be more compact than this. In any case, passing code around is very lightweight because code files are just text. Anyway, we'll call this model 2 so as not to interfere with our original model. Next, we call model2.loadState_dict and pass in the state_dict that we just saved. We get that by calling torch.load and passing in the file path where our model file is located. You can see that if your load is successful, it will say all keys match successfully. At this point, we would like to know, is our reloaded model the same as the model we saved? Luckily, this is an easy check, and we already know how to write this code. We just take our code from earlier to compute the accuracy of the model on the train set and test sets, but this time we'll use model 2 instead of the original model. As you can see, we get precisely the same accuracy as we did earlier. At this point, you might be wondering, so I just saved my model. It's in my local directory. But it's not my local directory. It's my Google Drive's local directory. What if my teammate asks me for this model? How can I share it? And that is the next question we are going to discuss. In fact, this is quite easy, and it's another reason I really like Colab. So over on the left here, you may have noticed this sidebar with some icons. If you click the folder icon, you'll see all the files in your current directory, including mymodel.pt, the model file we just saved. So let's right-click that. And now you can see that there's this option to download. And of course, that's how you can download this file to your local hard drive. Another option is to use Python code to download the file. Now, I've heard that this only works for Chrome, but of course that may change in the future. We can use the same module we used earlier for uploading files. So we import files from the google.colab module. Then we say files.download and pass in the file path. When we run this cell, the file is downloaded by our browser as usual. Alright, so that works as expected. In this lecture, we are going to look at the models we just used more in depth. Specifically, if you know a little bit about machine learning, you may recognize that the models we just used are called linear regression and logistic regression. We use logistic regression for classification, and we use linear regression for regression. So this lecture will look at how these models work and also explain why we refer to logistic regression as a neuron. Just to remind you of the high-level picture here, deep learning is the study of neural networks, and neural networks are networks of neurons. So you can think of these as the basic fundamental unit of computation in deep learning. Let's start with linear regression. In its most basic form, linear regression just means line of best fit. As you may recall from your high school math studies, a line has the equation y hat equals mx plus b. Here, x is the input variable, m is the slope, and b is the y-intercept. When we put these together, we get the equation for a line. Our job, of course, is to find the line that best fits our input data. To give you a simple example of how we would use linear regression, let's suppose we are trying to predict your salary based on how many years of experience you have. So in this case, x would be the number of years of experience, and y would be your salary. Now you might be wondering, what is the interpretation of the slope and y-intercept in this scenario? Well, let's try to play around with this equation a little bit and see what happens. We know that b, the y-intercept, is the value of y hat when x equals 0. So in other words, if you have 0 years of experience, this would be your salary, b. If x equals 1, that means you have 1 year of experience, and then your salary would be m plus b. If x equals 2, that means you have 2 years of experience, and then your salary would be 2m plus b. In other words, m is the increase in salary that you get for each additional year of experience. Of course, in the real world, we might want to make a prediction about your salary based on multiple factors. Instead of just years of experience, we might have another input, let's say average industry salary. So now your salary can also depend on what industry you are working in. So we'll call years of experience x1, and we'll call average industry salary x2. In this scenario, we would write out our model as y equals w1 x1 plus w2 x2 plus b. In this equation, w1 and w2 are called the weights of the model, and they are essentially the slope for each of the individual inputs, x1 and x2. Luckily, the interpretation is the same as what we saw previously. W1 is the increase in salary when x1 increases by 1. W2 is the increase in salary when x2 increases by 1. B is the salary when both x1 and x2 are 0. Another way to think of the weights is that they tell us how important each input is to predicting the output. Imagine the extreme scenario where we have some w sub I equals 0. In this case, it doesn't matter how much we increase or decrease x sub I, the output will not change at all. So in other words, x sub I has no influence on the output. That's another way of saying x sub I is irrelevant. Now imagine that w sub I is very large in magnitude. Note that it can be either very positive or very negative. This means that x sub I has a large influence on the output, because a small increase in x sub I leads to a large increase in the output. That's just another way of saying that this input feature is very important. Also, the sign of w sub I controls the direction of the influence. If w sub I is very positive, then an increase in x sub I will lead to a large increase in the output. If w sub I is very negative, then an increase in x sub I will lead to a large decrease in the output. Now, in what way is any of this related to neurons? Well, to understand this, you have to understand a little bit about biology. A neuron is a cell in your brain. You can think of it, as we said before, as the fundamental unit of computation. Neurons can talk to other neurons using electrical and chemical signals. So if you picture a neuron, you can imagine that there are many other incoming neurons attached to it. These input terminals are called dendrites, as you can see in this image. Those incoming neurons might come from, say, your eyes, or your ears, or your nose, or your hands. So if your eyes see something, an electrical signal goes along the nerves in your eyes and travels to your brain. The same thing happens when you hear something, or you smell something, or you touch something. Now remember, we're picturing a single neuron. It's taking in inputs from a lot of different places. Now this neuron, it has to decide if it's going to pass this signal on to outgoing neurons. Because remember, this neuron's kind of in the middle. There are some neurons going into it, and it's going out to some other neurons. Now, how does it do that? Well, it does that in a very similar way to linear and logistic regression. It sums up all the incoming signals, and then this summation becomes the outgoing signal that gets passed on further down the chain. The next thing you have to know is that not all neuron connections are created equal. Some connections are strong while others are weak. Some connections excite the receiving neuron, while other connections inhibit the receiving neuron. This is just like the weights of a regression model. A large weight, either positive or negative, has a strong influence on the output. That's a strong connection. A small or nearly zero weight has only a weak influence on the output, so that's a weak connection. A positive weight influences the output in the positive direction, so that's like an excitatory neuron. And a negative weight influences the output in the negative direction, so that's like an inhibitory neuron. The signal that gets passed along neurons has a special name. It's called an action potential. Basically, it's a spike in electrical potential. So if you measure the electrical potential over time, at a particular point in the neuron, you would see a signal like this. Now, action potentials don't behave in a very intuitive way. In particular, you can think of them as binary outcomes, just like logistic regression. In other words, the neuron is more like logistic regression than linear regression, although the linear regression equation is the main calculation that takes place in both cases. So here's how the action potential works. Basically, we're going to sum up all the influences from all the incoming neurons. If the electrical potential of this sum is greater than some threshold, then an action potential will propagate through the receiving neuron. If the electrical potential is less than this threshold, then nothing happens at all. This is very much like binary classification, where we make predictions which are either 0 or 1. In biology, we call this the all or nothing principle. Either an action potential fires or it doesn't. As you can see here, when the stimulus is too weak, there's only a little bump in the response, so those are not action potentials. But once the stimulus reaches a certain threshold, a full action potential spike occurs. So there's no such thing as a spectrum of action potentials, like an action potential of 1 volt, 2 volts, 3 volts, and so forth. Instead, it's just a binary decision. You get a spike or you don't. The incoming signals summed together are strong enough to generate the next action potential, or they will simply be ignored. So that's how you can think of logistic regression as a neuron. Each x sub I is an input from some incoming neuron. Each w sub I is a weight that tells us how strong the connection with x sub I is, and the sign of w sub I tells us whether that connection is excitatory, meaning it positively influences an action potential, or inhibitory, meaning it negatively influences an action potential. The weighted sum of each x sub I, which is then added to the bias term or threshold, is then passed through the sigmoid function. Once the sigmoid function is rounded, we get either 1 or 0, telling us whether or not an action potential should occur. In this lecture, we are going to answer the question, how does a model learn? Let's start with linear regression. In its most basic form, linear regression just means line of best fit. As you may recall from your high school math studies, a line has the equation y equals mx plus b. Here, x is the input variable, m is the slope, and b is the y-intercept. When we put these together, we get the equation for a line. And our job, of course, is to find the line that best fits our input data. So you can imagine that our input data is a bunch of data points that approximately create the shape of a line. This plot is called a scatter plot. So for each point x and y in our data set, we're going to draw a dot on this chart. Our goal is to find the line that best passes through all these data points. In practice, this means finding the slope and y-intercept. One method you may have used in high school is to take a ruler and to try and draw the best line on paper using visual inspection. Of course, since this is data science, we no longer use such methods. We have to be more systematic. The line that you draw might not be the same as the line that I draw. And furthermore, if we are in multiple dimensions, this won't be a line at all. So it's clear that we need something better and more quantitative. The idea is we're going to define an error function. For each data point, which is a pair made up of the input xi and the target yi, we're going to calculate a prediction y hat I equals to mxi plus b. Then we are going to take the square difference between yi and y hat I. We're going to do this for each of our data points for I equals 1 up to n. Once we've done this, we can add them all up and divide by n. This is called the mean squared error. It's the average squared deviation between our predictions and our targets. Basically, this is going to tell us how accurate our model is. If our predictions are equal to the targets, then this error will be 0 because yi would be equal to y hat I. Then, the more wrong we are, the larger this error becomes. So that's generally how an error function should work. As a side note, since some students get confused by this at first, we have multiple names for this error, and we usually use them interchangeably. Sometimes we call it a loss, sometimes we call it an objective, or sometimes we call it a cost. However, these all mean the same thing. I like the term cost because it makes intuitive sense for business people. As any good businessman would do, your job is to minimize your cost. And in fact, this statement alone tells us how to find the weights W. So how do we minimize this cost, or in other words, make it as small as possible? Well, it's time to turn to our old friend calculus. If you recall, we can find the minimum or a maximum of a function by finding where its derivative is equal to 0. If you're not convinced by this, try to draw a curve which has a minimum or a maximum, and draw the slope at the minimum or maximum point. If you drew your line correctly, it should be a horizontal line, meaning that the slope at this point is 0. And remember, the slope at each point is just the derivative, so that's why we want to find the derivative, set it to 0, and then solve for the parameter in question. Now, usually, we have more than one parameter. Even in one-dimensional linear regression, this is the case because we have both the slope and the y-intercept. So what happens when we have a function of more than one variable? In this case, the derivative is actually called the gradient. If you recall from your calculus studies, the gradient is just a vector or tensor of partial derivatives. For each of the variables, we're taking the gradient with respect to. So for example, if you take the square function in one dimension, that's called a parabola. But if you have two input dimensions, it's called a paraboloid. Beyond that, we can't picture it, but the basic idea is still the same. Find the gradient, set it to 0, solve for the parameters. By the way, the term parameter is just another name for the weights. So that's the W and B we've been referring to throughout this section. Luckily, in this course, we won't be calculating any derivatives manually, since I have many other courses which do that a lot. And by a lot, I really mean a lot. So in this course, we're kind of excused from doing that, because PyTorch already does that for us using a process called automatic differentiation. Luckily, you don't have to know how that works either, because as its name suggests, it's automatic. So the only thing you really do have to know is that A, PyTorch is going to automatically find the gradient of all your weights, and B, PyTorch uses these gradients to train your model. At this point, you might be wondering, if all I have to do is find the gradient and set it to 0, then why in our previous code did it involve an iterative training process? Recall that we had to specify the number of epochs to train for, and this resulted in a plot of loss per iteration, which we could check to confirm that the training algorithm converged nicely. Well, in actuality, it's not possible to actually solve for the equation that you get when you set the gradient to 0 most of the time. The one exception to this, in this course at least, is linear regression, where we can solve it. We call the solution an analytical solution or a closed-form solution. Basically, this means that we can express the optimal value of W and B using an equation. For logistic regression and the rest of the models we'll be discussing, it's not possible to do this. Therefore, we need another approach. That approach is called gradient descent. Now, there's a lot more to gradient descent than what's in this lecture, and you can check out the in-depth section of this course for that if you're interested. For now, let's just talk about the basics. Essentially, what we do is we start at a randomly initialized point for both W and B. Since this is random, these probably don't lead to a small cost. So then we find the gradient of our loss with respect to W and B. We then take small steps in this direction to update W and B on each iteration. Remember, these iterations are called epochs. Mathematically, you can prove that this leads to a decrease in cost, although we won't discuss that in this lecture. You can imagine that this is exactly what goes on inside the optimizer.step function. This is really all that's happening. For epoch and range epochs, and then set W equal to W minus eta times the gradient of J with respect to W, and set B to B minus eta times the gradient of J with respect to B. So again, all we're doing is taking small steps in the direction of the gradient with respect to W and B. Now, one obvious question that arises from this is, how small should these small steps actually be? Well, the step size is specified by this Greek letter eta, which we call the learning rate. This specifies how fast or slow we want to train our model. It's important to set this value right, because if you don't, then your model won't get good results, even if your model is actually a good model. Unfortunately, there's no direct method of choosing a good learning rate. Generally speaking, the learning rate is something we call a hyperparameter. This is to differentiate it from W and B, which are just regular old parameters. It's called a hyperparameter because it's still a parameter, but it's not a parameter of the model itself. It's sort of like a meta parameter. And in fact, no hyperparameters are really chosen directly. It's more of a process of trial and error, along with intuition that you gain from practicing a lot and seeing a lot of different examples. As mentioned before, one way to know if your learning rate is too high or too low is to check the loss per iteration after training. This is somewhat unfortunate because training can take a long time, and you only know the result once it's done. If you use a bad learning rate and got bad results, well, you still had to wait for them. I really like this visualization because it encapsulates how to choose the learning rate quite well. If your learning rate is too high, then your loss will just shoot off to infinity. Intuitively, this is because you're overshooting the minimum and just ending up on the other side of the canyon. That means your steps are too large and you need to make them smaller. Sometimes your learning rate might be a bit too high, so you'll see some convergence, but it'll converge to a suboptimal value. If your learning rate is too low, then you'll see a really shallow curve. This is also not good because, as I mentioned, training takes time. So if your learning rate is too low, you'll have to wait longer. But not only that, sometimes you can just get stuck at a suboptimal point. That's also not good. A good learning rate is in between these two extremes, and so what you'll probably end up doing is finding the limits of your particular dataset, what's too high, what's too low, and then trying different numbers in between until you find something good. Normally, we try numbers that are powers of 10. For example, 0.1, 0.01, 0.001, and so forth. In this lecture, we are going to look at an alternative and better way of building a logistic regression model in PyTorch. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. The motivation behind doing this is that when we perform the sigmoid, we have to do an exponential operation. The problem with that is that exponentials are numerically unstable due to the fact that they grow very fast with respect to the input. In addition, the log term in the binary cross entropy is also unstable for similar reasons. Well, it turns out that because the binary cross entropy loss has a log in it, it almost cancels out the exponential in some sense. Although we won't go through any derivations in this course, the end result is that if you know you have to do both the sigmoid and then the binary cross entropy loss right after, there is a way to combine them into a single function so that you avoid numerical instability. In particular, you can express the loss only in terms of the activation, which is also called the logit in this case. If you've ever studied statistics, then you may have heard of this term before. Otherwise, don't worry. Basically, the logit is just the input into the logistic function, and the logistic function is just another way of saying the sigmoid function. So in this script, pretty much everything is exactly the same, except in two places. The first place is when we create the model. So before, we used the sequential and combined the linear layer with a sigmoid layer. But in this script, we no longer need the sigmoid since that's included in the cost calculation, and therefore our model goes back to being just a linear model. The output of this model is the logit. Then, when we create the loss function, we use BCE with logit's loss instead of BCE loss like we were earlier. As its name suggests, this function calculates the binary cross entropy loss directly from the logits. As you can see, everything after this is the same as well. So our training loop is the same and we get the same results. One more difference we have to pay attention to is when we make predictions. If you recall, the sigmoid always outputs a number between 0 and 1, and we interpret that as a probability. So when we want to make a prediction, we simply round those probabilities. Anything greater than 0.5 is a prediction of 1, and anything less than 0.5 is a prediction of 0. But what do our predictions look like now, since the output can again be any number? In this case, we just go back to our geometrical picture. You can also think of what the sigmoid actually does, and if you follow that logic, this should make sense. If you recall, anything on one side of the hyperplane, defined by our model, is positive, and anything on the other side is negative. The sigmoid simply maps all the positive numbers to probabilities greater than 0.5, and similarly, it maps all the negative numbers to probabilities less than 0.5. Thus, it's very easy to make predictions. We simply check if the model output is greater than 0 or less than 0. Anything greater than 0 is considered a 1 prediction, and anything less than 0 is a 0 prediction. Note that we can use the greater than sign directly, even though the greater than sign returns trues and falses. As we discussed earlier, in Python, true is 1 and false is 0. Therefore, we don't need to do any further processing. Once we have our predictions, we can check the model accuracy, and again we can verify that the result is the same. In this lecture, we are going to talk a little bit more in depth about training sets versus validation sets versus test sets. First, let's think about why we would want to split our data up in the first place. As usual, I'm going to return to my dumb as possible picture, which is that machine learning is nothing but a geometry problem. Imagine that all the data I collected in the past looks like this. So I find a line that can discriminate between the two classes of data, and I can conclude that my classifier has pretty good accuracy. Great. But remember, what's the point of building a classifier? It's to use it on unseen data that I want to classify in the future. So what happens when tomorrow's data looks like this? Now all of a sudden, the classifier is no good. In fact, it's terrible. Well, that sucks because this is actually the data I really care about classifying. I don't care about classifying past data. Why? Because I already know what the answer is, so there's no need to classify those data points anymore. Now you might think this example is a little extreme. Clearly the data we have seen so far in this course did not behave this way. When we get good training accuracy, we tend to get good test accuracy. But in fact, we'll see some data that behaves exactly like this later in the course. Here's another image that should help you understand why we need train and test sets. The problem is overfitting. If you have a complex enough model, you will get very good accuracy on almost any dataset. But you can see here that although we fit very well to the training data, we have a poor fit on the test data, which in this case is the true function that we are trying to model. This is called overfitting, and it's the opposite of what we want, which is good generalization. There's a trade-off that must happen here. Should you make your model more complex so that your training accuracy is improved? Or should you make your model less complex so that there's a better fit to the test data? The problem is, if your model is not complex enough, then it will perform poorly on both the train and test data. So your job is to find the optimal amount of complexity such that it performs well on the test data. It can't be too complex, but it also must be complex enough. You may also know this as the bias-variance trade-off, although this concept is outside the scope of this course. You're encouraged to check out the in-depth series if you're interested in learning more. So I hope that satisfies your intuition about why we need to have separate data for both training and testing. Now, you may have heard that sometimes people split their data into 3 separate data sets: the train set, the validation set, and the test set. What's the difference? Why is it that sometimes we just have train and test, and sometimes we have train, validation, and test? It's really just semantics. When you have a train and test set only, your test set is more like a validation set. In fact, the words test and validation are pretty much synonymous. They mean the same thing linguistically. What you are doing when you split your data into train and test is you are actually using your test set to validate that your model works on unseen data. So in fact, sometimes when people split their data into 2 parts, they'll call them train and validation sets rather than train and test sets. In this context, the meaning of both is exactly the same. I hope you're not confused. So in what case will we want to distinguish between train, validation, and test? For this, I like to think of Kaggle contests, although it's well known that Kaggle contests are not a good representation of how you will do machine learning in the real world. In fact, there have been multiple instances of cheating on the platform. In any case, the way that Kaggle works is this. You will have some data that Kaggle gives you to train your model on. These are typically labeled as train and test. Importantly, the test set does not come with any labels, so you can't compute your model's performance on the test set by yourself. This is unlike when we split the data into train and test in our class. All you can do with your test set is make predictions and submit them to Kaggle servers. Then, Kaggle will show you your test score, along with the test scores from other participants. They will list these on what is called a leaderboard. This is the true test set because it's how Kaggle is testing your model. But if that's how Kaggle tests your model, then how will you test your model? This is where the validation set comes into play. Remember, Kaggle, generally speaking, although this is not always the case, will give you just a train and test set. You want to perform well on the test set because if you win, then you'll make some money. So you have to make sure that your model performs well on unseen data, namely this test set for which Kaggle withholds the labels. In order to do that, you have to pretend to evaluate your model on unseen data by splitting the train set that Kaggle gives you into train and validation sets. For this data, you do have all the labels, and so you can calculate both the train and validation accuracy. Sometimes, although this isn't usually done in deep learning, you will split your data randomly into train and validation sets multiple times. We call this cross-validation. Here's the basic idea. Let's suppose you split your training data into 5 parts. Then you'll do a loop which runs 5 times. On each iteration of the loop, you'll consider 4 of the parts to be your train set and the remaining part to be your validation set. On each iteration, you will train a new model on the current train set and evaluate the model on the current validation set. When you're done, you'll have 5 different validation scores, and from this, you can calculate the mean, variance, and so forth to get some statistical measure of how well your model might perform on unseen data. The reason this isn't used for deep learning is that the datasets are usually so large and training takes so long that the variance is pretty small, and just one validation set should give you a pretty good idea of your model's performance. There is a small caveat to the leaderboard. In fact, there are 2 leaderboards, the public leaderboard and the private leaderboard. The public leaderboard is where your score on the test set is shown. The private leaderboard uses yet another dataset, and this is the one on which the winner of the contest is selected. This is of course to prevent overfitting to the public leaderboard test set. The public leaderboard allows you to submit a solution multiple times, so you have some chance of overfitting to it. On the other hand, you only know your private leaderboard placement once, at the end of the contest. So in fact, to confuse you even more, now there is not just the train set, the validation set, and the test set, but there is yet another test set. Of course, Kaggle is not the real world. In the real world, your test set is the set of data for which you really want the answer, but you can't produce using non-machine learning techniques. If you could just write a basic computer program or implement a simple set of rules, then you don't need machine learning. So when we are using machine learning, it's because we really do not know the answer, or we can't compute it practically. Some basic examples of this are fraud detection, spam filtering, or object detection. We really want these to work on data that we haven't seen before, but it's clear that we can't do that work manually. The next question I want to answer is, what is the validation set even for? You might be thinking, sure, I can evaluate the model to get some idea of how it will perform on unseen data, but then what? What do I do with that result? How is it actionable? Recall that in machine learning, we have a lot of choices. We call these choices hyperparameters. For example, in gradient descent, we have to choose the learning rate. We can't learn the learning rate. As you learn more about different variants of gradient descent, you will have to choose between those variants, and then among those variants, there are yet more choices of hyperparameters. If you have a lot of input features, you might want to choose just a subset of the features so that the model can learn from the important features rather than just the noise. You also have to choose between different model architectures. After you learn about basic linear models, you'll learn about ANNs, CNNs, RNNs, and so forth. You'll have to choose the number of layers in a network and the number of units in a layer. You'll also have to choose activation functions. There are so many choices, you will feel overwhelmed. Unfortunately, it's not possible to choose these hyperparameters automatically. You can't just do gradient descent on model architectures. At this stage, your approach amounts to just trial and error. And so, how do you evaluate each of these different choices? The answer is by using the validation set. Typically, you will pick the model that gives you the highest validation score, and that will be the model that you use on your test data, whether that's a Kaggle contest or pushing your model to production. In this lecture, we are going to start looking at machine learning from a new perspective. While this example might seem overly simplistic, you might be surprised to learn that every example that we do in this course will rely on these basic steps which you are about to learn. First, let's start by describing the basic task. I'm sure you're all familiar with this example from your grade school science and math classes. Let's suppose we've done some kind of scientific experiment. For example, we measured the voltage in a circuit with different resistors, or we asked everyone in our class what their height and weight is. This gives us a dataset with two columns of numbers, one that we can call x and the other that we can call y. Now imagine that we plot these points on a grid and we get something that looks pretty close to a line. We would like to draw a line on this grid that closely passes through these points. In your grade school class, maybe you did something like took a ruler and moved it around a little bit until you found the best possible line. But now that we're doing machine learning, we need more sophisticated methods than just drawing dots on paper and using a ruler to estimate what the best line should be. The problem is, what happens when we have thousands or millions of dots? What if our data is more than two-dimensional? Then this approach is no longer possible. So perhaps you might say, aha, I know what to do. Let's use our trusty tool, scikit-learn. As you know by now, this is what a basic regression script might look like if we were to use scikit-learn. First, we load in some data, call that x and y. These would just be the two columns of data that we were looking at earlier. Next, we create a model. For the coming lectures, we'll be interested in linear regression, so let's create a linear regression model. Next, we call the fit function to fit our model to the data. Next, we can do multiple things with our fitted model, such as making predictions with model.predict. The problem with this is just using an API, but it doesn't tell us how any of this actually works. What actually happens inside these functions, and why is that important to know at this stage? What I want to highlight on this screen is what we should expect to be different when we look at PyTorch. First, model creation is going to be different. As I mentioned earlier, PyTorch is going to allow us to build all kinds of different models using composable building blocks. So it's not going to be some predefined model as in scikit-learn. Next, I want to emphasize in PyTorch, there is no such thing as a fit function or a predict function. This is unlike TensorFlow and Keras, which do provide you with those functions. So if you're looking for something simpler, then TensorFlow or Keras may be more your pace. In PyTorch, however, that will not be the case. Therefore, we're going to have to find out how to do all these steps in PyTorch using our knowledge of the concepts. Importantly, however, this lecture will focus only on the concepts and not on any PyTorch. In the next lecture, we'll look at how to actually implement these concepts in PyTorch syntax. So let's first look at what these concepts are before we discuss the details. I'm going to go out of order in some sense, but you'll see why that has to be the case. The three main concepts we want to discuss are, number one, what is the model architecture? And how do we actually build a model if it's not defined for us, like it is in scikit-learn? Number two, how do we make predictions with the model? In fact, this is closely tied to number one. And number three, how do we fit the model? That is, how do we find the slope and intercept parameters? As you'll see, this is the most complicated step. It also depends on number one and number two, which is why we have to discuss this last. So number one, what is the model architecture? Well, you already know this. It's y hat equals mx plus b. Notice our use of the hat symbol here. Typically, we'll use y for the true value, also known as the target, which is given in the dataset, and y hat for the corresponding prediction. Fortunately for us, this actually solves both of the first two problems for us. This not only defines the model architecture, which is a line, but it also tells us how to make predictions. Given some input x, I can see exactly how to calculate y hat. Pretty simple. So this is our model, y hat equals mx plus b. The hard part is number three. How do we actually find good values of the slope m and the intercept b? The key is to define what is called a loss function. I warn you that there are many synonyms for the loss function, and you'll see them all. So don't be afraid if you see these different terms and think one of them might be wrong. That's not the case. These words are all used equivalently. So you might see this referred to as a cause function, or an objective function, or an error function. These all mean the same thing. The basic idea is this. If we pass in our data set x and y, along with some setting of m and b, the loss function will tell us how good that setting of m and b is. Let's see how. First, let's assume that we're given a set of pairs of data points, x1, y1, x2, y2, all the way up to xn, yn. Make a note to yourself now that it will be convention for us, and many others, to use the capital letter N to represent the number of samples in your dataset. This is not always the case, but it's at the very least the convention I use and the convention many others use. So if you see something different in the future, or you've seen something different in the past, don't freak out. Believe it or not, this happens sometimes. Anyway, the idea behind linear regression is, we will not find a line that perfectly passes through all the points. That's impossible, since as you can see, there is no such line that can pass through all the points. All we can do is try to find a line that is a good fit. So how do we define a good fit? As I mentioned, this is called a loss function. I'm going to start by telling you what it is, and then describing to you why it makes sense. For some of you, it'll make sense immediately, and for others, it might not. But hopefully by the end of this, I will have convinced you that it does make sense. So the loss function that we use in regression is called the mean squared error, or MSE for short. Basically, you take all the yi's, and you find the squared difference between them and the line itself, the y hat i's. You can think of this as the squared vertical distance from each yi to the line. Each corresponding point on the line is a y hat I, a prediction given xi. Once we have all the squared differences, we take their average. You all know how to find averages, so you know that it's just the sum of the squared differences divided by the total number of points n. The question is, why does this make sense? I think this is a great exercise to try for yourself if you haven't done so before. Take a piece of graph paper and draw some dots and a line, just like what you see here, and calculate the squared error by hand. What you should discover is that if the line is not a good fit, then the error will be larger. If the line is a good fit, then the error will be smaller. I think that's pretty intuitive. In addition, you should recognize that if the data points perfectly lie on the line, then the mean squared error will be 0. Next question. How do we use this loss function and our model to actually find the values of m and b? Let's see what happens if we plug in our expression for y hat into the loss. This is clearly the equation we would get. Now I have a quiz question for you. What are the variables in this equation? I'll give you a second to think about it, so please take a moment to come up with the answer before moving on to the next slide. Okay, so I hope you thought about the answer to what the variables are in this equation. If you said x and y, this is not correct. Many beginners make this mistake because in a typical math course, the variable is x, and you're always trying to do something like solve for x. However, it's important to recognize that in machine learning, x is normally not a variable. xi and yi are just values from our dataset. You can think of them as numbers from your Excel spreadsheet. In fact, in our case, the variables are m and b. Remember that these are the values that we are currently trying to find. They are unknown, and therefore they are variables. At this point, we know that our goal is to minimize the loss with respect to m and b. This is how we would write that mathematically. If you're afraid of math, don't worry about this equation too much because it doesn't give us anything new. It's just a way of saying what we already said, but using math. We would like to find the best values of m and b, called m star and b star, where these values of m and b are the ones that minimize the loss L out of all possible values of m and b. How do we solve such a problem? . It might help to consider a similar but simpler problem. Say we have a function f of x equals x squared, a quadratic. We all know this from high school. You might say, well, I can just look at the graph and see that the minimum value is 0 when x is 0. But remember, we don't do that in machine learning because in machine learning, we work in multiple dimensions. You can't just look at it. At this point, we have to introduce our old friend, calculus. If you recall, the way that we solve this is you find the derivative, df by dx, set it equal to 0, and solve for x. This is because, as you can see, the derivative at the minimum is equal to 0. So if you draw a tangent line at the minimum point, it should be a horizontal line. There are, of course, a lot more details that I'm not including here, but you should at least remember this from your high school math studies. So how do we find the solution in our case? Since we have two variables, m and b, we have to take partial derivatives. But the idea is the same. Find the partial derivative of L with respect to m and set that to 0. Find the derivative of L with respect to b and set that to 0. This will give us two equations with two unknowns, which are m and b, at which point we can solve for m and b. In fact, if you've never done this before, I would encourage you to do this calculation and solve for m and b as an exercise. This can be done for any arbitrary dataset, x1, y1 up to xn, yn, so your solution should be in terms of those values. There is a problem with this approach, however. Unfortunately, finding the derivatives and setting them to 0 only works for linear regression. It does not work for any other model we will discuss in this course. In fact, the very next model we discuss, for linear classification, cannot be solved in this way. Instead, we need to use a method called gradient descent. Very briefly, the gradient is the multi-dimensional analog of the derivative. So basically, when you're working in multiple dimensions, you have gradients in place of scalar derivatives. The idea behind gradient descent can be understood with this simple picture. It's an iterative algorithm, so we're going to go in a loop. On each iteration of the loop, we're going to take a small step in the direction of the gradient. It's been mathematically proven that if we keep doing this, we will eventually end up at the minimum point. In this lecture, I don't want to get into detail about gradient descent. However, you are encouraged to check out the lectures in the in-depth section of this course if you are interested. Our goal is to get to how we do this in PyTorch as quickly as possible. Gradient descent is a really cool algorithm because it works in pretty much all cases. That's why libraries that have automatic differentiation, such as Theano, TensorFlow, and PyTorch, have been so popular for machine learning. Aside from deep learning, you can use the exact same techniques for things like hidden Markov models, k-means clustering, matrix factorization, and more. Alright, so since this has been a pretty long lecture, let's recap the steps. Our goal in this lecture was to take you from the 3 steps of the scikit-learn API to what actually happens conceptually. As you recall, the 3 steps are creating the model, fitting the model, and making predictions with the model. After this lecture, you now understand at a high level what actually happens during these 3 function calls. However, the concepts don't provide the full picture because we still need to implement this in code. In fact, I have a course that goes very in-depth into all these concepts and how you can take them and put them into a computer program using basic libraries like NumPy in the Python programming language. But remember, this course is about PyTorch, so the next question we have to ask is, how is this done in PyTorch? Concepts are one thing, but syntax is another. For example, the syntax for PyTorch will be different from the syntax for TensorFlow, even if we are doing the exact same thing. In this lecture, we are going to do what I call code preparation. It's like the in-between step that will help us get from theory to code. So we know what each of the steps are, and we know conceptually how they work. The next question is, what's the right syntax in PyTorch to actually make it work? I like to think of this like how I think of learning programming languages. I hope everyone in this class knows Python, since that's the language we'll be using. So let's say what I want to do is print the numbers from 0 to 9 inclusive. I know how to do that in Python. It's just for I in range 10, print I. But let's say that now I want to learn how to do this in Java. If you know Java, just pretend that you don't for a moment. What's the situation now? Well, I understand the concept. The only challenge is, what is the Java syntax for it? I know the concept, but I don't know the syntax. So let's look at the syntax. Looking at this, all the components should feel very familiar to you, even if you've never seen it before. I can see the keyword for. That's the same in both languages. That tells me I'm doing a for loop. Same concept, different syntax. I see the index variable I. Again, it's the same concept in both languages. In a for loop, I might have an index variable, something that iterates as the loop progresses. I see a lower limit and an upper limit. The lower limit is 0 and the upper limit is 10, which are inclusive and exclusive respectively. Same thing in Python, except that the lower limit is implicitly 0 in Python, so you don't have to specify it unless you want something other than 0. Finally, I see that inside the loop, we again have the same concept, printing, but again, just with a different syntax. So I hope you get the analogy here, which is that, number 1, concepts and syntax are separate things. You might know the concepts, but in different libraries, the syntax will be different. Number 2, since we already know the concepts, our next task is to ask, what is the syntax? What I want you to realize at this point is that, while this is the most simple script from this course, it is also the most important. You're going to notice a pattern in this course, which is that, no matter how complex what we do is, these steps will essentially remain the same. Remember that what we want to focus on right now is, number 1, how do we build the model? Number 2, how do we train the model? And number 3, how do we make predictions using the model? Let's start with number 1, how do we build the model? At this stage, it's going to be very easy. Just one line of code, model equals nn.linear11. What this means is that we want a linear model with one input and one output. The first argument is for the input size, and the second argument is for the output size. There are cases where the input and output might be sizes other than 1 and 1, but we'll see those later. Right now, we're interested in doing simple linear regression, where there is one x-axis and one y-axis. Next up, number 2, how do we train the model? If you've ever used other libraries such as Keras and scikit-learn, you might assume this would be easy in PyTorch, but unfortunately, it doesn't encapsulate all the steps as you would expect. Luckily, thanks to the concepts we just learned, that will help us in understanding this syntax. The first step in training the model is to define a loss and an optimizer. As we discussed, the loss that we need for linear regression is the mean squared error, and there just so happens to be this object called MSE loss in PyTorch. Typically, we call this object a criterion. There's one interesting thing to notice here, which is that this is a bit of an exercise in what I call API hunting. If you think only about the concepts, you know the equation for the MSE loss. If I gave you the y's and the y-hats, you could calculate this loss yourself. But in PyTorch, it's not a matter of knowing the formula. It's a matter of knowing the syntax. So you need to find the right object that implements the loss you were looking for, and then do the right things with that object. At the same time, it's nice to know a little bit about the concepts so that you actually have some sense of what's going on. Next, we have the optimizer. There are many such optimizers in PyTorch, but the simplest one is called SGD. When we create the SGD object, we pass in two arguments, the model's parameters, which we get by calling the convenient function model.parameters, and the learning rate. As a side note, SGD stands for stochastic gradient descent. Again, in these lectures, I'm not so concerned about what's going on mathematically, but rather the syntax. If you'd like to understand what's going on mathematically, I would encourage you to check out the in-depth sections of this course. Alright, so at this point, we've defined a loss object and an optimizer object, but we haven't yet done any computation with them. As you recall, gradient descent involves doing a loop, and inside the loop, you repeatedly apply the gradient descent equation. So that's essentially what we want to do right now, but in PyTorch. So obviously, we need a loop. Usually, we call each iteration of the loop an epoch. Unfortunately, it's not so easy as simply translating this one line of mathematical expression into one line of code. There are multiple steps in the code that have to be done. The weirdest part just happens to come first. We have to call optimizer.zeroGrad. At this stage, I like to think of it just as some boilerplate code, something that needs to be done. So just put it there and forget about it. If you want to know what it does, then what we can say is that, internally, PyTorch accumulates gradients whenever you call loss.backward, which is a line that shows up later in this loop. Personally, I would not worry about that because 99% of the time, we'll be doing exactly what you see here, and so far, none of the examples in this course require you to actually accumulate gradients. The rest of the steps are relatively straightforward. As you know, in order to calculate the loss, we need the predictions, the y-hats. In order to get those, we pass them into our model. This allows us to see the functional aspect of PyTorch. Even though the variable model is an object of type linear, as you recall that's what we created earlier, it can be used as if it were a function. So when we pass in some inputs into the model and call it like a function, we get the model outputs. The next step is to pass the arguments and the outputs into our criterion, the mean squared error. Again, this is an object, but we're using it like a function. The next step is to call loss.backward. Conceptually, you can think of this as calculating the gradients. For example, the partial derivative of L with respect to M and the partial derivative of L with respect to B. The final step is to actually apply the gradients using the gradient descent equation. As you'll see later, there are a lot of variations to the basic gradient descent, so once you have the gradients, there are a few different things you can do with them aside from just this. Now you may have noticed something strange in the previous code snippet. Previously, I called the data x and y, but in the previous code snippet, I used the variable names inputs and targets. Is this just a matter of some trivial renaming, or did I really mean to say that they are different things? In fact, they are different things. When I load in the data, I usually call the inputs x and the targets y, and usually they are NumPy arrays. But one important detail that we haven't looked at yet is that PyTorch does not work with regular NumPy arrays. Instead, PyTorch works with torch tensors. These are basically arrays, but they are special arrays that are part of the PyTorch library rather than the NumPy library, so they have some special functionality. So some conversion has to take place before you pass the data into your model. In the following example for simple linear regression, the steps are what you see here. First, we're going to reshape x and y to be n by 1 instead of just n. In machine learning, we typically assume that our data is two-dimensional, with the number of samples along the rows and the number of dimensions along the columns. This applies even for the targets, which is not the case in libraries such as Keras or scikit-learn, so be aware of that. Second, PyTorch is really picky about data types. It won't allow you to multiply a float32 by a float64, which is also known as a double, so you have to be mindful of this also. By default, if you don't specify anything, PyTorch will create all your variables as float32s. In NumPy, if you don't specify anything, your arrays will be float64s. So before we create torch tensors, we're going to cast our NumPy arrays into float32. The final step is to call the function torch.fromNumPy. This takes as input our NumPy arrays and returns corresponding torch tensors. So these are the inputs and targets we were working with in the previous training loop. The final step is to make predictions. You might think we already did that in the training loop when we called model of inputs. But the important thing to remember is that PyTorch only works with torch tensors, and the inputs variable is a torch tensor. It's reasonable to assume then that the output is also a torch tensor. Of course, if you want to do any later processing, such as plotting the array with matplotlib, you might want to have a numpy array rather than a torch tensor. Therefore, in addition to actually calculating the output, you'll also want to convert it back into a numpy array. Normally, you can do this just using the numpy function. However, PyTorch also does some stuff behind the scenes, where it creates a graph and keeps track of the gradients in the graph. Basically, you can just call the detach function before you call the numpy function in order to detach that tensor from the graph. Alright, so that was our code preparation for simple linear regression. I said this before, but it's worth repeating. While this is the simplest example in the course, it's also the most important because it introduces a lot of new concepts, mostly about how to use PyTorch. In future examples, we'll just be repeating these same concepts over and over again, so you'll get lots of practice. You've seen that PyTorch is quite a bit more complicated than simply instantiating a model, calling fit, and then calling predict. In this lecture, we are going to do an example of simple linear regression in code using PyTorch. In other words, we are going to learn how to find the line of best fit. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. To start, we're going to do a few imports. You'll see throughout the course that these imports are what we'll need pretty much every time. So we have torch and torch.nn, which is a module that contains a lot of useful stuff in PyTorch. Next, we have numpy and matplotlib. Numpy is for doing linear algebra, and matplotlib is for doing plotting. Next, we're going to generate some data to apply our model to. Now you might ask, why aren't we using real data? Well, don't get too excited. That's what we're going to do next. Using synthetic data is actually very important in machine learning, but more on that later. So to generate this data, I'm going to set n equal to 20 data points. Remember that our convention is to use the capital letter N to represent the total number of samples and the capital letter D to represent the total number of features. As we move on to more complex datasets later in this course, there will be some additional letters. In our case, D equals 1, so we don't really need to specify anything. Next, we're going to generate some random points on the x-axis. They're going to be uniformly distributed between -5 and +5. There are, of course, several ways you could do this, so if you don't like the way I've done it, you can feel free to implement your own. And this applies to anything in this course. So what we've done here is generated 20 random data points using the random function, which outputs random numbers between 0 and 1. Next, we multiply those numbers by 10, so that they'll range between 0 and 10. Finally, we subtract 5, so the range becomes -5 to +5. Next, we're going to generate the data points on the y-axis. Because we're doing linear regression, we would like these y data points to be linearly correlated with the x data points. So to do that, I'm going to say y equals 0.5 times x minus 1 plus some Gaussian noise. Pay close attention to these numbers. This means that our true slope is 0.5 and our true y-intercept is -1. These are the values that our model is going to try and find. Now you might ask, why have I added Gaussian noise with mean 0 and variance 1, rather than some other kind of noise? In fact, when we have Gaussian noise, the mean squared error becomes the correct loss function to use, and thus, since we're using the mean squared error as our loss function, we would also like to use Gaussian noise centered at 0. You're not expected to understand this during this course, but when I mention these things, people inevitably end up asking me why this is the case. So if you are interested in learning the answer, I would recommend you look at the in-depth series of courses where I've already covered all this material. Next, we're going to do a plot of the data.
As you can see, it sort of roughly forms a line. It's a little bit hard to tell since the noise variance is quite high compared to the variance of the data itself, but I think it's pretty clear that the data is trending upward. So that's everything for our data set. Next we have the PyTorch stuff. First we're going to define our model. As promised, it's just one line, nn.linear11. This means that we're creating a linear model with one input and one output. Next, we're going to begin the training process. As you know, this starts with defining a loss function object and an optimizer object. Luckily, you've seen this before, so there are no surprises. We're using the MSE loss and SGD optimizer with a learning rate of 0.1. Next, we're going to transform x and y into data types which are appropriate for PyTorch. So we start by reshaping x and y into n×1 matrices. Next, we cast both x and y into float32s and convert them into torch tensors. In the next block, I've printed out the type of the input's variable, so you can see that it is indeed a torch tensor. Next, we have our main training loop. To start, we set n epochs, the number of iterations of the loop, to 30. Now you might ask, why did I choose 30 and not some other number, like 10 or 5 or 1000? Well, the trick is, I've ran this script before and tried different values already. As a student, you don't really see all the work that goes into choosing hyperparameters. You only see the final result. So you might assume that you can just pick any number and everything will work out great. This is often surprising for beginners. In any case, I discuss a lot about hyperparameters elsewhere, so if you're interested in that, please ask me about it on the Q&A. Something else you didn't see in the code preparation lecture is that I have a list of losses that I'm going to plot after we are done. In each iteration of the loop, we are going to store the loss in this list, and at the end, we're going to plot the loss per iteration. This will let us understand whether or not we chose good hyperparameters and whether or not the training process converged and so forth. So it's quite useful. Oh, and just a hint for future examples. We are pretty much always going to plot this after training. So I don't want anyone asking me, what does this plot mean? Because it's going to be the exact same thing every time. So don't forget it. Alright, so next we have our training loop, which we've seen before. As I mentioned before, the first step is this weird step. We zero the gradients. And this is because, behind the scenes, PyTorch is actually accumulating the gradient each time you call backward. So this will zero the gradient to prevent them from accumulating and give us the correct answer. Next, we do a forward pass to get the model predictions. Since you've now seen how to make predictions and get the output as a NumPy array, you know this is similar to that, except we don't need to take the additional step of converting this into a NumPy array. This is all in PyTorch land, so we get out a PyTorch tensor that we can apply in the next step. The next step is to calculate the loss, using the criterion we defined earlier. Next, we save the loss to our list of losses. In this case, we do want to take the loss from PyTorch land into Python land, so we call the function item. Now you might ask, why do we call the function item and not the function numpy like we do when we make predictions? And that's because the loss is a single Python number and not a numpy array. So when your tensor is a single number and you want to bring that number back to Python land, then you should use the item function. Next, we calculate the gradients. PyTorch encapsulates this in a function called backward to be called from the loss tensor. Finally, we call optimizer.step to do one step of gradient descent. As always, I like to print out useful information while the loop runs. So here you can see I'm printing the iteration number along with the corresponding loss at each iteration of the loop. So if you look at these numbers, they give you some sense of how training is progressing. But the real value comes from plotting the loss per iteration, which is what we have next. This is the kind of curve we like to see in deep learning. A steady decrease downward, fast at the beginning and slow at the end. This plot gives us more confidence that training has completed successfully. It's not a 100% guarantee, but this is at least one positive sign. Next, we're going to use our trained model to make predictions and plot the result. As you recall, our task for this model is to find a line of best fit. It would be quite silly if we didn't actually plot that line. The next step is therefore to pass our inputs into our model, which gives us the predictions in terms of a torch tensor. Since we would prefer to work with NumPy arrays, we first detach the tensor and then call the NumPy function. Now you might be wondering, what happens if I do not call detach? We'll look at that in a moment. The next step is to plot the data points using a scatter plot and then to plot the predicted line using a line plot. As you can see from the result, our line is in fact the line of best fit. Next, we look at what will happen if you do not call the detach function. As you can see, we get an error. It says, can't call numpy on variable that requires grad. Use var.detach.numpy instead, which is exactly what we did. However, this error message gives us a hint for an alternative way to make predictions. We can see that it has something to do with gradients. In the next block of code, we can instruct PyTorch not to compute gradients. We use the context manager with torch.nograd. Inside the block, we make our prediction, but if you notice, there is no call to the detach function. As you can see, the output is printed correctly without any error. The last thing we would like to do in this script is to inspect the parameters of the model to check if they are close to the true values. As you recall, these are the slope and intercept of the line. In machine learning, we call this the weight and bias. In order to get these values, we call model.weight.data.numpy and model.bias.data.numpy. Intuitively, you can expect that model.weight and model.bias store the weight and bias as some special PyTorch tensor variable. However, we would like to bring these back to NumPy land, so in order to do that, we call data.numpy. You can imagine that the reason we treat these differently from the model's predictions is because they are model parameters rather than data inputs or outputs. If we look at the values, we can glean a few key pieces of information. First, the obvious thing we want to check, are they close to the true values? We get 0.46 and minus 1.2, so it appears that they are. One interesting thing about these is that W seems to be a two-dimensional array, whereas B seems to be a one-dimensional array. You might ask, why do we need a 2D array and a 1D array to store single numbers? In fact, we don't, but we need our model to be flexible enough to handle different scenarios. These scenarios are what you'll learn about in later lectures. The final thing I want to talk about in this lecture is, what is the point of using synthetic data instead of real data? This is going to come up once or twice in this course, so it's good to discuss this early and often. One of the most important questions we can ask is, does our model actually do what we think it does? As a beginner taking a course, your automatic reflex is to make a guess, or to think of the problem philosophically. But this is not a philosophy course. It is a computer science course. We don't discuss maybes in this course. It's binary, yes or no. It works or it doesn't. So synthetic data is very useful in that regard. I can create synthetic data such that if my model does what I say it does, then it will find the pattern in the synthetic data that I set it up to find. If it can, then my assertion is wrong. Doing things this way allows us to test the strengths and weaknesses of our models and to help us understand what they can and cannot do. In the next couple of lectures, we are going to see how easy it is to apply what we just learned to a real-world dataset. In fact, this real-world dataset is one of the most significant datasets of all time. This lecture is about Moore's law. As you recall, Moore's law is the observation that the number of transistors per square inch on integrated circuits doubles approximately every 2 years. In other words, roughly speaking, computing power grows exponentially. Some futurists, such as Ray Kurzweil, have observed that this pattern applies to technology as a whole, so that even when Moore's law runs out for transistors, perhaps some new invention will appear to take its place. Maybe that will be quantum computing, AI, or something we can't yet imagine. Now you might be thinking, wait a minute, this isn't linear at all. If something grows by a constant factor over a given period of time, that's actually exponential growth. For example, it will grow from 1 to 2, 4, 8, 16, 32, 64, and so on. We can write the generic equation for exponential growth as c equals c naught times r to the power t. Here, c is the output variable, and that's the thing we're counting. C naught is the initial value when t equals 0. T is the input variable, which in our case represents time. And finally, r is the rate of growth. You can see that if t increases by 1, then c increases by a factor of r. This holds true for all time periods. So if I'm at t equals 1 going to t equals 2, I can find the next value simply by multiplying by r, and similarly for going from t equals 2 to t equals 3. Luckily, by taking the log of the count variable, we can turn this into a linear equation. Basically, we take the log of both sides, and we show that the log of c is a linear equation with respect to the time t. This is exactly what we want. So if we use linear regression on the log of transistor counts with respect to time, we should find that the rate at which transistor counts double is approximately 2 years. If you can't see how this works right away, it might help to substitute the variables in the previous equation with some more familiar variables. So let's replace log c with y. This will be the output variable. Let's replace log r with a, the slope. Let's replace t with x. This will be the input variable. And finally, let's replace log of c naught with b, the intercept. Now we just have y equals ax plus b, which is our linear equation from earlier. Note that I'm using the letter a instead of m for the slope, which is perfectly okay. At this point, the problem becomes exactly the same as our previous problem. As long as we can transform our dataset into a quote-unquote Excel spreadsheet, which has the log of transistor counts in the y column and the year in the x column, then our code for building, training, and predicting with the PyTorch model should be exactly the same as it was before. This is what we mean by all data is the same. As you will see, there is no difference in the model between this example with transistor counts and the last example with synthetic data. And you might wonder, why do I say this so often? And really, I just go by how often I get asked. So it's really you, the students, who guide what I say. If I find that a lot of students have a problem with something, then I will emphasize that point more often. So despite the fact that I repeat this constantly, students will still sometimes ask me, can you do an example on such and such dataset? And my response is, as always, the code is exactly the same, no changes are needed. Although, because this message is pretty effective, I think it definitely has helped a lot of students understand the idea a lot better. There is one caveat to this, which you will see in the following lecture. In order to use linear regression or any other kind of model in this course effectively, you should make sure your data is either normalized or in a small range of values and centered around 0 or at least near 0. In order to do this, we're going to subtract the mean and divide by the standard deviation. This makes it so that the sample has mean 0 and variance 1. Please note that in this course, we will use the terms normalize and standardize pretty much interchangeably. Standardize is a term that is used more in statistics, and it refers specifically to the case where you take a sample and transform it so that it has mean 0 and variance 1. This is opposed to the term normalize, which could refer to standardization, but is a more general term overall. For example, it could mean transforming your data so that it stays in the range 0 to 1. This is not the same as having mean 0 and variance 1. On the other hand, in cases like batch normalization, which you'll learn about later in this course, it does refer to the standardization operation. The real question is, why do I mention this as a caveat? Here's the problem. We're doing 2 transformations on our data. This is going to make it more difficult to prove that transistor counts double every 2 years. So here's a quiz question for you. Given that the equation for exponential growth is c equals c naught times r to the power t, what does r have to be in order for the transistor count to double every 2 years if t is in units of years? I would strongly recommend you try to figure this out for yourself before we move on to the next lecture. The next question you want to consider is, if we take the log of both sides of this equation, how does that value of r relate to the slope of the line? And finally, if we normalize the data in both the x and y axes, how does that affect the slope and intercept of the line? We'll go through these calculations in the next lecture in detail, but the main point is, we are not going to get the answer directly just by fitting a line to the data. For example, just because the transistor count doubles every 2 years, this does not mean the slope of the line is going to be 2. It's going to be related to the number 2 somehow, but to find out exactly how, you have to do the math. In this lecture, we are going to look at the Colab notebook that performs linear regression in order to prove Moore's law is true, that the transistor count doubles approximately every 2 years. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. To start, we're going to have all the same imports as before, with one additional import, which is pandas. Pandas is useful for working with CSV files, which is the format our data happens to be in. To obtain the data, we are going to use the wget method to get the CSV file hosted on my GitHub. Next, we are going to load in the data. The data doesn't contain any headers, and it only contains 2 columns. I would recommend verifying that this is the case. The next thing we want to do is reshape X so that it's a 2-dimensional array of size n by 1 rather than a 1D array of length n. We also need to do the same thing for Y in PyTorch, although this generally doesn't extend to other libraries. Remember that the convention is X is a 2D array of size n by d, and Y is a 2D array of size n by k, where k is the number of outputs. Next, we are going to do a scatter plot of this data. Notice that it shows exponential growth, which we already know. So next, we're going to take the log of y, which is what we discussed previously. We see that we get back what looks like a good candidate for linear regression. Next, we are going to do a little bit of pre-processing on the data. Specifically, we're going to standardize or normalize x and y. We'll want to keep these means and variances around for later use. So let's call them mx for the mean of x, sx for the standard deviation of x, and similarly for y. What we have to keep in mind is that, by doing this, the units of x and y no longer make sense. Previously, x had units of years, but this is no longer the case, and y had units of log counts, which is no longer the case. We'll have to reverse the transformation later on if we want to get back to the original units. In the next plot, we do a scatter plot again, which on first glance looks exactly the same as it did before. But if you look closely, you'll see that both the x and y axes are centered around 0, and the range of values is now small, which is exactly what we want. Next, we're going to do a little more pre-processing to convert our data into float32. Next, it's time to create our linear regression PyTorch model. Thanks to our rule, all data is the same, this code will be exactly the same as before. Once we have our model, which is just one line of code, we're going to create our loss and optimizer. As you can see, there's one argument here that might be new to you, momentum. This is one of those variations on gradient descent that I was talking about earlier. If you want to know more about these, you're encouraged to check out the in-depth section of the course. Next, we're going to convert our NumPy data arrays into torch tensors using the fromNumPy function. Next, we're going to run our main training loop. As promised, this is the exact same thing as what we had earlier, just with a different number of epochs. I just want to mention again, because a lot of people ask me, how do I know what number of epochs are needed? Just remember that there is no way around trial and error. There is no magic formula. You just have to keep trying until your loss per iteration looks right. You'll be seeing the same loop over and over again throughout the course, so each time I'm going to spend less and less time explaining it. Alright, so from the loss values it's printing out, it looks like the loss has converged. Alright, so next we're going to plot the loss per iteration as usual. And from this we can confirm that our loss has converged. Next we're going to plot our line of best fit. Again, this is the same as before, so there's no need to explain this code again. As you can see, our line is indeed a line of best fit. Next, let's get the trained weights of the model. You already know how to do this. It's model.weight.data.numpy. As expected, it's a two-dimensional array that holds a single number. The question is, what does this number even mean? To answer that question, we need a little theory. Let's start by recalling our model of exponential growth. We have c equals c naught times r to the power t. As you recall, we convert this into a linear equation by taking the log of both sides. So now we have log c equals log of c naught plus log r times t. If we rename the variables, we can make this look a little more familiar. So let's call the input x, the output y, and the slope a. A good thing to remember is that the slope of this line is the log of r, not r itself. We can leave the intercept term untouched because it's not related to the rate of growth. It's just the initial value of the count. Next, we have to take into account that our data is normalized. As you recall, we normalize the data using the equations we see here. Let's call the transform data x prime and y prime. So y prime is equal to y minus my divided by sy, and x prime is equal to x minus mx divided by sx. Now we can begin to understand our own model. Our own model is also just a line, just with different units and therefore a different slope and intercept. So let's call the parameters of this line w and b. So the line that we actually fitted would be y prime equals w times x prime plus b. What we can do next is recover our original model by substituting x prime and y prime with their expressions in terms of the original variables x and y. So now we have y minus my divided by sy is equal to w times x minus mx divided by sx plus b. You should be able to see intuitively that this is still a linear equation. After doing some algebraic manipulation, we can isolate y in terms of all the other variables. If you don't understand how we got to this step, I would strongly recommend trying this on paper by yourself. What we can see is that there is one term involving x and 3 other terms not involving x. Clearly, the 3 terms not involving x are equal to the intercept log of c0. Remember, we don't care about that because that doesn't involve the rate of growth. Instead, what we care about is the slope. Luckily, it has a simple expression. It's just w times sy divided by sx. We know that our original line has the form ax plus log of c0, and therefore we can conclude that if we had fitted a line to our original data, the slope would be a equals w times sy divided by sx. Alright, so the next question we want to ask is, what is the value of a? Luckily, we know w, we know sy, and we know sx. So we can just plug them in to find a. Remember that w is a two-dimensional array holding a single value, so in order to retrieve this value, we have to index w twice, at row 0 and column 0. We see that we get another sort of strange number, 0.34. It's not clear how this would lead to a rate of growth. That means the transistor count doubles every 2 years. Of course, that's because there is still more work to do. So let's go through a quick calculation. To review once again, our model for exponential growth is the count c is equal to c0 times r to the power t. c0 is the count when t equals 0, and r is the rate of growth. If we take the log of both sides, we get an equation that's linear in t. We can express this in terms of our usual linear regression variables, y equals ax plus intercept. This shows us that y is equal to log c, a is equal to log r, x is just the time t, and the intercept is log of c0. Because a is equal to log r, we can just take the exponential of both sides to get that r is equal to e to the power a. From here, we can plug in the value for the slope that we found to get that r is equal to 1.407. Although, as you'll see, we won't need to use this value directly. Next, let's consider the doubling time, or in other words, how long it takes for c to double. We can do this by thinking of the original equation as the original time and the original count. This origin is completely arbitrary, and as you'll see very shortly, its values don't actually matter. So in order to double this count, the left-hand side would become 2c, and on the right-hand side, the time would just be t prime. We call it t prime because we don't know what it is yet. That's what we're trying to solve for. So if we take these two equations and divide one by the other, we see that the c disappears. The c0 also cancels out. And as I promised, the origin point doesn't matter. We get 2 is equal to r to the power t prime minus t. T prime minus t is actually the time duration that we care about. That's how long it takes for the transistor count to double. How far from t is t prime? We can rearrange this to get that t prime minus t is equal to log 2 divided by log r, which is equal to log 2 over a. Since we found a, this is just a number. And more importantly, it's a constant number. One important note is that the defining characteristic of exponential growth is that the growth rate does not change over time. In other words, the value of t itself doesn't matter. This same equation holds no matter what the value of t is. This is like saying the duration from t to t prime is always constant, and as you can see here, it's always log 2 divided by a. So in the next block of code, we can print out this value. Log 2 divided by a is approximately equal to 2, just as Moore's law says it should be. Therefore, we've confirmed that Moore's law is true. In the final block for this notebook, I have a little exercise for you. In this lecture, one of the most difficult parts was transforming the data using standardization and then reversing that transformation. And you might ask yourself, is that really necessary? So the exercise for you is to find out what happens if you don't try to normalize the data. You might assume that since the data falls on a line, it should be pretty easy to apply linear regression, as we've done multiple times so far. So give that a try, and I'll see you in the next lecture. In this lecture, we are going to discuss a tiny bit of theory related to linear classification. Previously, we discussed linear regression. As you recall, this is the task where our goal is to find a line or curve of best fit. You want your model to output predictions which are close to the data points. In classification, this is not our task. In classification, we do not want the line to be close to the data points. Rather, in classification, our goal is to separate data points into distinct classes. Although we can consider the case where we have more than two classes, we'll start with two since that is the most intuitive. Because this is linear classification analogous to linear regression, our model is still a line. It's just that the job that we want this line to do is different from regression. Unlike regression, we don't care if this line is close to the data points. Instead, we want the line to separate data points of different classes. In other words, if one class consists of the red dots and one class consists of the blue dots, then we want all the red dots to be on one side of the line, and we want all the blue dots to be on the other side of the line. In this way, we can say that the line discriminates between the two classes. As you can see, this is not related at all to having the line be close to the data points. Also, I hope I haven't lost you in terms of what the colors of the dots mean. Remember the rule, all data is the same. So for one particular data set, the color might represent whether a credit card transaction is fraudulent or not. For another data set, the color might represent whether an email is spam or not. For another data set, the color might represent whether a student will graduate or not. And as you can see in this example, it represents disease versus healthy. As with the previous lectures, we are going to start from a very basic perspective. How would this work in scikit-learn? We're going to learn what each of these steps mean in terms of concepts, and we'll also learn how each of these steps are done in PyTorch. Remember that in PyTorch, there is no model constructor, or fit function, or predict function, so we have to do all that ourselves. To recap, here are the steps we do in a typical machine learning script with scikit-learn. First, we are going to load in some data. We call that x and y. Next, we're going to instantiate a model. Next, we are going to train or fit the model using model.fitxy. Next, we are going to make predictions with the model using model.predictx. This can be the same x or a different x, for example, xtrain or xtest. Finally, we can evaluate our model using model.scoreXY. For classification, this score returns the classification accuracy. And just to reiterate, this lecture is all about answering the question, what actually happens inside these functions? This question is really important to answer because you'll notice that if you compare this to linear regression, literally nothing has changed except for the name of the class. So really, what happens inside these functions makes all the difference. It's what really matters if you want to know how this stuff actually works. As a side note, if you're a beginner and you don't yet know what classification accuracy means, here's a quick definition. As you know, our model is a binary classifier. It's predicting spam or not spam, for example. Therefore, its predictions can only be right or wrong. There are no other possibilities. Either it's right or it's wrong. The classification accuracy, then, is simply the number of predictions I get right divided by the number of total predictions. The classification error is the number of predictions I get wrong divided by the total number of predictions. It should be easy to verify that the classification error is equal to 1 minus the classification accuracy. Also, note that you can calculate the accuracy and error on both the train and test sets. So you can speak of the train accuracy and the test accuracy, which would be evaluated on the train set and the test set respectively. So the first concept we want to consider is, what is the model? More accurately, we want to ask, what is the model architecture? As usual, it helps to look at a picture. So here's a typical picture of a linear classification problem. We have some data points, and we want to separate the data points of different colors with a line. As a side note, why do we call this linear classification? Well, you will notice that the word line actually appears in the word linear. This surprises many people, so don't worry if you haven't noticed this before. Alright, so what's the equation for a line? I claim that a line can be expressed using the equation w1x1 plus w2x2 plus b equals 0. Now at this point, you might sigh to yourself and say, gosh, why does lazy programmer have to make everything so complicated? I already know that the equation for a line is y equals mx plus b. So why do we have to use this more complicated looking equation with w's and x1 and x2 and so on? In fact, we must. You'll see why this form of the line is useful very shortly. If this is new to you, I would recommend the following exercise. First, notice that all we've done is rename the axes from x and y to x1 and x2. This is important because these axes refer to the input data. If you recall, y is the target. For example, if we're going to classify images of cats versus images of dogs, then we might say dogs are the red dots and cats are the blue dots. But they are not an axis on this graph. So x1 represents the horizontal axis and x2 represents the vertical axis. Y is not an axis. This is different from linear regression, where the target y was an axis on the graph. Now that you know this, you should be able to rearrange the equation w1x1 plus w2x2 plus b equals 0 into slope-intercept format. What I mean by that is, have x2 on the left side by itself, and then you'll have some slope times x1 plus some intercept. Now it has the same format as y equals mx plus b, except that we use x1 and x2 instead of x and y. Also, note that the b that appears in y equals mx plus b is not the same as the b that appears in the other equation. So in this slide, I've called the intercept b prime to differentiate it from the original b. As always, if you can't immediately see how I got this, you should try it by yourself on paper so you know how to do it. It should only require elementary school algebra. The next question you might have is, how does this line help us make predictions? Luckily, due to the rules of geometry, if we plug in a data point x, which is not on the line, then either we will get a number bigger than 0 or less than 0. In fact, any data point on one side of the line will always give us a number bigger than 0. Any data point on the other side of the line will always give us a number less than 0. Using this, it's very easy to turn this into a prediction model. All we have to do is take in any data point x, which is a vector containing the elements x1 and x2, pass it into the expression for our line, w1x1 plus w2x2 plus b, and then check its sign. If the sign is positive, we predict 1. If it's negative, we predict 0. Mathematically, you can encapsulate this decision rule using the step function, or if you want to be less formal, you can think of it as the picture that you see here. We call A the activation, and if the activation is greater than 0, we predict 1, otherwise we predict 0. Now, as you may already know, in deep learning, we really like differentiable smooth functions. So rather than the step function, which is not smooth, what we do is take a smooth version of this called the sigmoid. The sigmoid is an S-shaped curve, and it maps the activation to a number between 0 and 1. We usually interpret this as the probability that y equals 1 given x. Then, when we want to make our prediction,
we just round this probability. So if the probability is greater than 50%, we predict 1, otherwise we predict 0. Again, this is called the sigmoid function, which is important to know for our implementation. As a side note, when we apply the sigmoid function on top of a linear function, we call this model logistic regression. This is because we also sometimes call the sigmoid function the logistic function, although this term is not really used too often these days. In addition, we also refer to the argument into the logistic function as the logit, but a more current and generic term for this is activation. You might realize that, using what we know so far, there is a little bit of a notational challenge. If we keep writing each component of x separately, we're going to run out of space. It's easy to write w1x1 plus w2x2 when there are only 2 components of x. But what if there are 100 or 1000? Luckily, we have a mathematical way of representing this. If we consider x to be a feature vector containing each component of x, and w to be a weight vector containing each component of w, then our expression just becomes the dot product between w and x. So we can write this in a much more compact way by saying probability of y equals 1 given x is equal to the sigmoid of w transpose x plus b.
Okay, so at this point, let's recap the 3 concepts we need to cover. Number 1, model architecture. Number 2, using the model to make predictions. And number 3, model training. We just covered number 1 and number 2. You know what the model architecture is, and you know how to use it to make predictions. Basically, given some input x, you know how to plug it into the previous formula to get some output prediction y hat. The final step is training. As I promised earlier, we are going to follow the exact same general steps as we did when we learned about linear regression. It may surprise you, but these are the same steps that we are going to follow for every subsequent example in this course. That's why I said it's the simplest example, but it was also the most important. Now you see why. So as you recall, we need to define a loss function. Then, after we've done that, all we need to do is apply the gradient descent procedure to update the parameters of the model in order to minimize that loss. Once we've completed training, we can plot the loss per iteration to ensure that the loss converts successfully, and we can test our model by checking its accuracy on the train and test sets. The main difference in the training process between regression and classification is that we have a different loss function. As you recall, in regression, our target is a real number, and our prediction is also a real number. In this scenario, it makes sense to use a loss like the mean squared error, or MSE. But in classification, our target is a category. Our model output is the probability that the input belongs to each of the categories. So the mean squared error doesn't make any sense in this scenario. In fact, for classification, what we want is the cross-entropy loss. There's one little wrinkle here, which is that we're doing binary classification, in which there are only 2 possible classes, and the corresponding loss is called the binary cross-entropy loss. In general, if your model can handle any number of classes, then you'll use the regular cross-entropy loss, but we'll discuss that later in this course. The reasoning behind the cross-entropy loss is quite a bit more complicated than the mean squared error, so we won't discuss that theory in this lecture. If you want to learn more, then you should check out the in-depth sections of this course. For now, all you really need to know is the PyTorch API, since as you recall, this course is not about mathematical theory, but rather how we do things in PyTorch. Therefore, your job really is knowing the right function to call and spelling it correctly. Indeed, in this computer science course, what matters isn't your math skill, but your spelling ability. To summarize this lecture, we went over the concepts behind linear classification. Our goal was to consider these 3 things. Number 1, what is the model architecture? Number 2, how do we make predictions? And number 3, how do we train the model? As you saw, it was very similar to linear regression, in the sense that our model is still a line or a hyperplane, but it's how we use this line that's different. In regression, our goal is to get the line close to the data points, but in classification, our goal is to separate the data points. In regression, we just pass our data into w times x plus b, and that is our prediction. But in classification, we still pass our data through w times x plus b, we just have the additional steps of applying the sigmoid function and rounding the output probability. For number 3, again it was very similar to our previous example, where we set up a loss function and then use gradient descent to find the weights that minimize it. But the difference in classification is that instead of using the mean squared error, we use the cross entropy, and in our special case of binary classification, we use the binary cross entropy. In this lecture, we are going to do code preparation for our linear classification script. This example will look at a new classification dataset, so this lecture will go over loading the data as well. To recap, here are the general tasks that we need to complete. Number 1, load in the data. Number 2, create the model. Number 3, train the model. And number 4, evaluate the model. Let's start with loading in the data. For this example, we'll be looking at the famous breast cancer dataset. This dataset happens to be included as part of the scikit-learn API. You'll notice that in this course, we'll be looking at quite a few pretty famous datasets. These datasets are so famous that they are often included in various machine learning libraries, so there's no need to download the dataset as we did in our previous example. Of course, there will be plenty of examples in this course where the data do not come from libraries, so you'll get experience with each. Loading in data from scikit-learn is super easy. We just call the function loadBreastCancer, which returns a data object. This data contains the x's and y's, so we'll need to access them using the object's attributes. In particular, the inputs can be accessed using the data attribute, and the targets can be accessed using the targets attribute. There are 2 ways we'll want to pre-process the data before using it. First, the data isn't normalized. You already learned from our earlier example why this is a good idea if you did the exercise I suggested. Therefore, we will use the scikit-learn module standard scaler to normalize it. Second, we'll want to split the data into train and test sets. Intuitively, this is because we want to get a good idea of how the model will perform on data it hasn't seen before, not on data it has already seen. For the data we've already seen, we already know the answer, so machine learning isn't necessary. The data we really care about is the data we have not seen. For example, if you build a fraud detector, you want to be able to ask your model whether a new transaction is fraudulent. This is important because your model might do very well on data it's already seen, but poorly on data it hasn't seen. We'll discuss this more in a later lecture. In any case, this code shows you how to do both of these steps. Notice how we already use this idea of train test splits with the standard scaler. We fit the standard scaler on the training data only, and we apply the standardization on the test data using the fitted mean and variance of the training data. Once we've prepared our data, it's time to build the model. As you know, the linear classifier is almost the same as linear regression, just with one extra step, the sigmoid. This should be a hint that we're still going to have a linear object somewhere in the model. Well, it just so happens that the sigmoid is also represented in PyTorch with an object, the sigmoid object. It should make complete sense then if we combine the linear object with the sigmoid object in sequence. And in fact, that's exactly what we've done. PyTorch allows you to easily stack these computation steps in sort of a wrapper object called sequential. What you're telling PyTorch is, I want my model to apply these functions in this order. And the functions we want to apply in this case are the linear model, then the sigmoid. There's one detail here that I want you to notice, and this is that when we create the linear layer, the input size is d, while the output size is 1. As you recall, our data matrix is of shape n by d, where n is the number of samples and d is the number of features. So we'll have one input for each feature column in the dataset. In addition, we have one output, which represents the probability that the output should be classified as a 1. The next step is to train the model. As promised, we are still doing gradient descent, which means nothing about our gradient descent loop is going to change. We still do our zero grad, get the output, calculate the loss, call backward, and do one step of a gradient update. What's different is that we'll be using a different cost function, but also a different optimizer. As mentioned previously, our loss function for binary classification is the binary cross entropy, which is performed in the object BCE loss. In addition, we'll be using the atom optimizer, which has become the go-to default in deep learning in recent years. Normally, I would say that the gradient optimizer you choose is like a hyperparameter, so you should always experiment to see what works best. In practice, many people simply choose atom by default. This does not mean that atom is actually guaranteed to work best, so you should still try other methods and observe the results yourself. If you want to learn more about atom, you're encouraged to check the in-depth section of this course. And if that's still not enough, then you'll want to go through the in-depth course where I discuss this algorithm in detail and build it up from scratch. The last thing we're going to do in our script is evaluate the model. This is different in classification compared to regression. In regression, we use the mean squared error as our loss, but we also use it as our evaluation metric. It kind of makes sense, since I don't think any other metric would be significantly more advantageous. The mean squared error is kind of a natural way to look at the regression error. Alternatively, you could look at the root mean squared error, which is just the square root of the MSE, so that it's in the same units as the target. But still, taking the square root is kind of a trivial transformation. With classification, it's a different story. We have the cross entropy as our loss, which is not a natural or intuitive measurement. What we really care about is accuracy. Out of all my predictions, how many did I get right? And how many did I get wrong? So in order to evaluate our model, we're going to calculate both the train and test accuracy. This necessarily also involves making predictions with the trained model as well, so we'll learn how to do that too. Of course, it's not so different from how we make predictions with our regression model. We'll just need to round our prediction to 0 or 1, since the targets are encoded as 0 or 1. In this lecture, we are going to do an example of classification in code using PyTorch. Our problem for this lecture will be to predict whether a patient's diagnosis of breast tissue is malignant or benign. This is a classic application of machine learning, and deep learning especially has made great progress in this field. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. To start, we're going to have all our usual imports: torch, torch.nn, numpy, and matplotlib. Next, we are going to load in the data. This dataset is part of scikit-learn, so we're going to import the function load breast cancer from the module sklearn.datasets. Next, we're going to call this function and assign it to a variable called data. Next, we're going to check the type of the data variable, since it's not clear what it returns. We can see that it returns an object of type bunch. Luckily, I've already inspected this object, so I know that it acts kind of like a dictionary. In that way, we can call the function keys, and it's going to show us all the keys that we can access from this object. So we see data, target, target names, description, feature names, and file name. So the first two keys, data and target,
refer to the input data x and the targets y respectively. So I'm going to call data.data.shape to check the shape of x. Okay, so we see that it's 569 by 30, so that means we have 569 samples and 30 input features. Next, I'm going to print out the targets. Okay, so as you can see, it returns a one-dimensional array of zeros and ones as expected. Now, luckily, even though the targets are just zeros and ones, we can still determine what they mean by printing out data.target names. As promised, they stand for malignant and benign. Next, we can confirm that the length of y is equal to the length of x, 569. Next, note that we can also print out the input feature names as well. So we can see things like mean radius, mean texture, mean perimeter, and so forth. Of course, you're free to look up this dataset online if you want to learn more about it, but remember that we would just like to treat this as a geometry problem. Next, we're going to split the data into train and test. You'll notice that I'm importing things as we go along, since that helps tell the story. But in general, you'll find that it's more conventional to put all the imports at the top. So here we're going to import the function train_test_split from the module sklearn.modelSelection. Then we're going to call this function and make the test set 33% of the original dataset. This returns xtrain, xtest, ytrain, and ytest. Then we're going to assign the shape of xtrain to the variables n and d, which may or may not be useful later. Next, and this is important in deep learning, we want to scale our data. The basic idea behind this is that because the output is a linear combination of the input, you don't want one input to have a very large range, say 1 million, and another input to have a very small range, like say 0.001. If this happens, then the weights will be too sensitive when the input has a large range, and not sensitive enough when the input has a small range. So the typical way to deal with this is normalization or standardization. Basically, this just means subtracting the mean and dividing by the standard deviation. Luckily, scikit-learn already comes with a class for this called standard scaler. So we fit transform on xtrain, and then we transform on xtest. Remember that it's important not to expose any of our test data to the training pipeline. Next, it's time to do our PyTorch work. As you saw earlier, we first need to build a model object, which is now a sequence of modules. It takes in a list of two modules, linear and sigmoid. The linear layer has an input size d and an output size 1. As mentioned, we want to apply the sigmoid activation so that the outputs are in the range 0 and 1. Next, we are going to prepare to train our model. So we'll need a loss and an optimizer. The loss we're going to use is the binary cross entropy loss, or BCE loss, which is the appropriate loss for binary classification. The optimizer we'll use is called Atom, which is a common default chosen by deep learning practitioners. Next, we're going to convert our data into torch tensors before we enter our training loop. As you've seen before, this involves calling the function torch.fromNumPy. In addition, we still need to convert all the data to float32. One detail you may have missed if you're not accustomed to PyTorch is that we want to reshape the targets to be a 2D array of size n by 1 instead of just a 1D array of length n. In other libraries such as scikit-learn, Keras, and TensorFlow, a 1D array is appropriate, but that's not the case in PyTorch. Next, we have our main training loop. As promised, we're not going to spend much time explaining this because it's pretty much exactly the same as before. There's one small additional detail here, but it's one that doesn't require any new knowledge. Now that we have both a train and test set,
we want to be clear about which dataset we use where. So when we do the training portion, meaning a step of gradient descent, we'll want to use the train set, X train and Y train. This involves doing a forward pass, calculating the loss, calling loss.backward, and then calling the optimizer step. So you can see all these here. So we pass X train into model to get outputs. We pass Y train and outputs to get the loss. We call loss.backward and then optimize it as step. But on top of that, we would still like to know the test loss per iteration. This will tell us whether or not our model is overfitting. For example, if we see the test loss increasing during training, then we know that we are overfitting our model. To calculate the test loss, we do some of the same steps, but with the test data instead of the train data. So we do the forward pass, but we pass in X test instead of X train. Then we calculate the criterion with the test outputs against Y test. Finally, we save both the train loss and the test loss in our arrays of losses. Next, we check our loss per iteration. Everything appears to look good, and the train loss is not too different from the test loss, which means our model is not overfitting. Next, we check the accuracy of our model. Remember that, unlike with regression, the metric we care about is very different from the loss function we minimized in order to train our network. Accuracy is simply the number we got right divided by the total number of predictions. In order to get the train predictions, we first pass X train into the model, which gives us P train. We want to convert the output, which is a torch tensor, into a NumPy array by calling the NumPy function. These outputs are still probabilities, so we want to call np.round in order to convert them all to zeros and ones. Once we have our predictions, we can calculate the accuracy by doing a point-wise comparison with Y train and taking the mean. Now, this calculation often confuses beginners. How does this calculate the accuracy? I would encourage you to do a few simple examples in the console on your own if you don't get it right away. Remember that equals equals returns true or false. You'll get true if two items are equal and false if not. This operation happens element-wise, so if Y train and P train are arrays of length n, then doing equals equals will give us an array of length n that contains all trues and falses. So what happens when you take the mean of an array containing trues and falses? What does that even mean? Usually, it only makes sense to calculate the mean for numbers, and clearly true and false are not numbers. However, in Python, true is treated like 1 and false is treated like 0. So if you try 1 equals equals true in the console, that returns true. And if you try 0 equals equals false in the console, that also returns true. In other words, this is really like an array of zeros and ones. We have a 1 whenever you got the correct answer, and 0 whenever we did not. You should convince yourself that calculating the accuracy is the same as just adding up all the ones and dividing by n, which is also the same as taking the mean. If you don't get it right away, write it down on paper. Next, we do the same thing for the test set to get the test accuracy. The result is that we get about 98% accuracy on both the train and test set, which is very good. As an exercise, here is a nice thing to try. In Keras and TensorFlow, when you do a training loop, you will actually get two arrays of data back. One is the loss per iteration for both the train and test set, and one is the accuracy per iteration for both the train and test set. You'll notice that we did not plot the accuracy per iteration here. So for the exercise, you should try to modify this code so that during the training loop, we not only collect the loss at each iteration, but also the accuracy at each iteration. When the loop is done, you should be able to plot the accuracy per iteration. You should see that as the loss goes down, the accuracy goes up. This is usually the case. You might want to also think about what are the downsides of calculating the accuracy at each iteration of the loop.